Have you ever really stopped to think about how your code, your actual ideas, become something a computer can understand? It's not magic, not at all. It's actually this incredibly strict set of rules, kind of like a hidden language behind the language you're typing. So today, we're going to pull back the curtain on the two most fundamental concepts in all of programming: syntax and semantics. I mean, think about it. When you're talking to a friend, you can be a little messy with your words, right? They'll get what you mean. But a computer? It's the most literal friend you will ever have. It does exactly what you tell it to, not what you meant to tell it. So the real challenge for computer scientists was, and still is, how do we talk to these machines with absolute mathematical precision, with zero chance of being misunderstood? And this slide just hits the nail on the head. Look at the left side, a simple English sentence: I saw a man on a hill with a telescope. But hold on, who's got the telescope? Am I looking through it, or is he holding it? It's totally ambiguous. Now look at the code on the right, int x is 5. There is absolutely no other way to read that. It means one thing and one thing only: create an integer named x and give it the value of 5. That's the kind of crystal clarity we need. So how do we get that clarity? Well, the first big piece of the puzzle is something called syntax. The easiest way to wrap your head around it is to just think of it as the grammar of a programming language. It's all about the structure, where you put your semicolons, how you write a function, all that stuff. If you mess up the syntax, the part of the compiler called the parser just gives up. It literally can't even start to figure out what you're trying to say. Okay, but this leads to a really cool kind of philosophical problem. If we need these super strict, unambiguous rules for our code, how do we write down the rules themselves without any ambiguity? You see the problem? We needed a meta-language, a formal, precise way to define the grammar of our programming languages. We needed a language to describe other languages. And of course, that's exactly what computer science legends John Backus and Peter Narr came up with. It's called Backus-Narr form, or just BNF for short. You can think of it as the ultimate master rulebook for a language's grammar, written with such precision that a machine can understand it perfectly. No fuzzy interpretations allowed. And what's really cool is we can use this powerful tool for more than just code. So let's take a quick detour from programming for a second. We're going to use BNF to define something every student in India knows is a non-negotiable part of the morning: a proper breakfast. So here's our first rule. On the left, inside those angle brackets, we have breakfast. That's called a non-terminal. It's just a concept we're defining. That double equals symbol, you can just read that as is defined as. So this whole rule says a valid breakfast is defined as some kind of drink, followed by the literal words "and biscuit." Simple enough, right? But wait, what in the world is a drink? Our rulebook isn't finished yet, so we add another rule. The non-terminal drink is defined as either the literal word tea or, and that's what that vertical bar means, it's a choice, the literal word coffee. And boom, just like that, with these two little rules, our formal grammar now allows for exactly two valid breakfasts: tea and biscuit or coffee and biscuit. No confusion. So let's just recap that real quick. Every single BNF rule has this simple structure. You've got the left-hand side, which is the non-terminal concept you're defining. You've got the double colon equals in the middle, which just means is defined as. And then you've got the right-hand side, which is the definition itself, made up of terminals, the actual literal words, and other non-terminals, which point to other rules. All right, this is awesome. We've got a formal system to define perfect grammar. Problem solved. We can all go home, right? Well, not quite. This is where it gets really, really interesting. Is having perfect grammar, perfect syntax, actually enough to make a program that works? Let's take a look at this really simple bit of code. First line, we declare a constant variable called name, and we set its value to Palash. Easy. Then, on the very next line, we try to change the value of that same constant to Akash. Now, here is the absolute kicker. According to all the rules of syntax, this code is perfect. The grammar is flawless. A parser would look at this and give it a big green check mark. But logically, it's complete nonsense, right? You can't change a constant. It's like that famous sentence, "Colorless green ideas sleep furiously." The grammar is perfect, but the meaning? It's just nothing. It's gibberish. And that brings us to the second and equally important half of this whole equation: semantics. If syntax is the grammar, then semantics is the meaning. It's the whole other layer of rules that checks if your grammatically perfect code actually makes any logical sense and is going to do what you think it's going to do. So that leads to the obvious next question, right? We found a formal system, BNF, to lock down syntax. Is there something like that for semantics? Is there a formal way to attach meaning directly onto our grammar rules? And thankfully, the answer is yes. One of the most powerful ways to do this is with something called attribute grammars. Now, the core idea is actually brilliant in its simplicity. We just take our good old BNF grammar rules and we start attaching extra bits of info to them, things we call attributes, like a value or data type. Then we write semantic rules to say what to do with that info. Let's make that a little more real. Imagine we have a grammar rule for addition. An expression can be defined as an expression plus a term. With an attribute grammar, we bolt on a semantic rule just like this one. And all it says is, hey, to get the value of the whole expression, just add the value of the first part to the value of the second part. With that one little line, we have formally attached the meaning of addition to that plus symbol in our grammar. Now, this specific type of attribute is called a synthesized attribute. Think of it like building something with Legos. You start with the small, individual pieces at the bottom. Those are the leaves of your parts tree, your actual numbers. Then you start combining them, building up, moving upwards, creating bigger and bigger pieces until you get the final, completed result right at the top. The information flows up the tree, synthesized from the parts below it. So let's just put it all together side by side. Syntax, that's your structure, your grammar. The compiler's parser checks it, and the question it's asking is this written correctly? Then you have semantics. That's the meaning, the logic. The semantic analyzer checks that, and it asks, does this actually do the right thing? The best analogy is simple. Syntax is the spelling and grammar of your sentence. Semantics is the story that sentence tells. At the end of the day, the relationship is really simple. Syntax builds the skeleton of your program. It gives it form, it gives it structure. But it's semantics that breathes life into that skeleton, that gives it meaning and purpose. You can have a perfectly formed skeleton, but without that spark of life, it's just a pile of bones. You absolutely, positively need both to make software that actually works. And that leaves us with a huge question, especially now, we're all seeing AI tools that can write insane amounts of code. But are they just getting incredibly good at mimicking syntax, at building perfect skeletons, or are they starting to genuinely understand semantics, the why behind the code? The next big revolution in programming might not even be a new language, but the first AI that truly understands meaning. What do you think?